Good afternoon. In this time, we'll consider the canonical ensemble. Actually, equipartition theorem will be considered next week. This part is also another review of the previous semester. This topics is covered by the book of the Brundle and Brundle. It is chapter 4. Okay. Before the lecture, I recommend a website. This is made by Mark Newman. They provide some materials, computational physics by Python. I think everybody took a course of computational physics lectured by Sungmok Lee. So I think you already know the Python language, but if you don't know, then you privately visit this website and then follow the chapter of this lecture. It is very easily written, so you can easily understand. In some case, in my lecture, you can make a code by the Python to solve some problem in the statistical mechanics. First is the canonical ensemble. In the statistical mechanics, we consider the microstates. Actually, statistical mechanics is considered state, microstate, and that is related to the macro quantity like temperature and pressure, etc. Here we give an example for the microstate. Here is you have 100 identical coins. Then you toss this identical coin simultaneously. Then you can obtain some configuration. Some coin is head and some coin is tail. Then you have a 100 coin here. Then you count the number of head, total number of head or total number of tails. Then here is some example. If you toss this 100 identical coin, you have a possible configuration, the number with 50 heads and 50 tails. That is, you have a total number of possible configuration is 100 factorial. However, if you say head 50 head, that you can exchange this order, then you have a count duplicate, so you need to this duplication numbers. So here is a head also 50 factorial, and tail is also 50 factorial duplication. So you divide by total number of possible configuration divided by this number of duplication. Then you can get it is 4 times 10 to the 27 possible configuration. We call this is a configuration. In some case, we will in the statistical mechanics, this configuration terminology of the configuration using as the same terminology as the ensemble. Then you have a possible number of case is here. This is example. This is example. For example, you have if you have 90 head and 10 tail, then it will be reduced sharply. It is 10 to the 27, but it is 10 to the 13. If you all coins have the heads, then that computation only one. So we can define some quantity. The quantity in statistical mechanics is described by some macro quantity as energy. For example, you can assign in this coin toss head corresponding energy 1 and tail corresponding energy -1. Then you obtain some total energy of the this configuration. Then this possible configuration corresponding to the some macro energy of the system. Then you can describe this possible number. Omega is a number of total number of microstates with energy E. In here, in this case, if I define the energy like this one, this configuration actually energy equal to 0. Then actually this is omega energy equal to 0 configuration, number of configuration. This is a micro stage and this is the macro stage. To the macro state energy 0, it has a number of configurations is this number, very huge number, has the same energy. In the quantum mechanics, it is degenerated states, like degenerate states. That is in statistical mechanics, it is ensemble or configuration. Okay. And we will consider some spin configuration or magnetic system in the later part of the in our lecture. Here is some possible microstates. Some atom or some nucleus has a spin, or if it has spin, then it has a magnetic moment. Then this magnetic moment, if you don't apply some external field at some finite temperature T, then each spin will be oriented random direction. In this configuration, there is some assumption because in some case magnetic moment and magnetic moment interact with each other, but in here their interaction is very weak. So only the agitation of the by the temperature is a strong effect of the orientation of the magnetic moment. Then in this case, if you don't apply external field, then each spin aligned randomly, then your total number of magnetic moment, that is a magnetization will be 0. That is a macro quantity. You have many possible configuration. This is one of the configuration. However, if you see some other time, then the configuration will be very different, having same magnetization. Similarly, if you apply some external magnetic field B0, then this magnetic moment actually each magnetic moment interact with the external magnetic field minus mu dot B. Here is magnetic moment is mu, and B is external magnetic field. Here is not. I don't use not. Anyway, then their single spin will interact with the external magnetic field like this one. Then in this interaction, the mu and p, if the external magnetic field this direction, then mu is equal to this same direction as the magnetic field, then their energy will be low energy because mu b. However, if external magnetic field this direction and spin is this direction, then their energy is mu b. So their energy is higher. And if magnetic field is here and some magnetic moment is different, some angle has aligned to some angle, then it is minus mu b cosine theta. So their energy is different to the aligned to the magnetic field. Then in this situation, their total magnetization will not zero. So shows the different macroscopic stage of the for the magnetization. This is also one of the micro stage of the system. Then if we know the all possible number of microscopic states, then you obtain the macro quantity like m or energy by the statistical mechanics. This is a key point of the in our lecture in this semester. Okay, this shows a similar problem, but in here spin A, B, C, D, E case. This case is spin is also only allowed to align up and down configuration. However, in this is all possible orientation in two-dimensional space. This if the spin is something like the up and down state, then you can count the total number of configuration like this one. If you n total n spin, then you have n factorial and up spin configuration and down spin configuration duplication of alignment. Then you can obtain the micro stage. Actually, this is a little bit different cases. Actually, this is actually ferry state. Ferry state means in B and C case, up and down spin absolute quantity of magnetic moment is same. However, in D cases, down spin is more stronger than up spin. So if all spin aligned like this one, this system shows some magnetization to the down direction. So it has a ferromagnetic, and even if they spin is aligned the opposite direction, they have some magnetization. Okay, here is some hypothesis for the statistical mechanics. In equilibrium, a system will appear to choose a macro configuration that maximize the number of macro states. Here is important key point is equilibrium. If your system is in equilibrium stage, this equilibrium stage they maximize the number of macro states, and system is choosing the maximized number of macro states. This is called microcanonical ensemble. That is described by each one of the possible microstate of system is equally occur. the same terminology is like this one. The system's internal dynamics are such that the microstate of the system is continually changing. That means if you have some gas particle like this one, you have there is many possible atom, molecule, gas molecule. Then they move some random direction and some velocity. Then they collide with each other. In some equilibrium state, the total energy of this system will be fixed. Then this molecule will collide each other. Then this is one of possible configuration. But if they microscopically, if they collide each other, then later time you have a different configuration. For example, in this particle collide with other particle, then it has a different direction, moving the different direction. Also other particles also different direction. Then however, this system is isolated, so they cannot lose the energy from the outside. So this configuration has same energy. So this is a member of ensemble, over the microstates. So they continuous change in this gas system. And third comment is you given enough time, the system will explore all possible microstates, and spend on equal time in each of them. This is called ergodic hypothesis. 우리말로는 에르고딕 가정, 에르고디성이라고도 하고, 우리말이 없어요. 그냥 에르고디성, 에르고디시티 이렇게 부르기도 하는데, this is called ergodic hypothesis. Then this is one configuration. Then this is another configuration, second configuration. Then in the phase space, you already learn about the phase space in classical mechanics. If you present this gas system to the phase space, then at fixed temperature E, for example, two-dimensional system, your energy, for example, your harmonic oscillator, your energy is E. Then harmonic oscillator actually rotate like this one in this circle. However, in the macro system, it has many particle number, so this phase space is very high dimensional space. For example, 6n dimensional space. That is in phase space. Then here is given energy E means in 6-dimensional phase space, you have some energy surface. Then in the energy surface E, one point is your corresponding microstates. Then dynamics means this state will moving under this energy surface. Then this particle will visit all possible microstates, and your staying time in here or in here, you have the same spending time. That is our microchemical ensemble. Okay, then let's define the temperature and thermal equilibrium by this configuration number. In our system, we have a thermal contacting system described by like this one. Actually, here one of the system is our system, and the other is actually corresponding to the some environment or heat reservoir. Anyway, if two systems in thermal contact means they can exchange some energy, exchange heat. If system 1 and system 2 is not in thermal equilibrium, they exchange some energy and their temperature will be changed. However, in the thermal equilibrium state, their temperature will be same. T1 and T2 will be same. That is equilibrium state. At the equilibrium state, system 1 is described as total energy E1 and system 2 is described by total energy E2. Then you have total number of microstates omega 1 and omega 2 at the each temperature. However, in here, our assumption in this thermal contacting system is they are system 1 and system 2 are interacting weakly interacting. Therefore, they interact with each other, so they can exchange heat. If they don't interact, they cannot exchange heat. This weakly interacting assumption, total energy of the combined system, this is our combined system, then total energy of our combined system is total energy E1 plus E2. We have no any other weakly interacting energy E1, E2. Only E1 energy is described by the system 1, and here is also described by the system E2. Maybe this thermal equilibrium assumption, this energy is adding each other, and then their total number of ensemble, number of states, total number of states is product of omega 1 and omega 2 because they are weakly interacting. So each state, for example, it is very similar. You have a coin and you have a dice. Then you throw coin and dice. Then they don't. When you toss these two coin and dice, then they don't influence to each other. Decide the number of states of the omega 1 tail or head, omega 2 dice 1 2 through the 6. So your total micro state is a product of omega 1 omega 2. Actually, this is actually our assumption of the thermal contact system. Then in thermal equilibrium, our previous thermal equilibrium, this number is maximized. Maximized means we have a total energy equal to E1 plus E2. So total energy is constant. So you have only one single independent variable, E1. Let's choose E1. Then your total derivation of this total number of states to the E1 is 0. This is extremum condition. However, here if you perform omega 1 omega 2, so if you perform the apply the derivative to each part, then you have this derivative plus this derivative. However, in here we exchange the variable. In here omega 2 is described by the function E2, so we use this variable of change. Then it is you have this is constant, so dE1, this is constant. So if you took a derivation dE1 plus dE2 equal to 0, so this one is minus sign here, so this is -1. So we have a condition like this one. What is this? This is rewritten this form. Omega 1 over d omega d1 is just a derivation of logarithm of omega 1 d1. Then we already know the actually the Boltzmann entropy. We in the previous semester we introduced the Boltzmann entropy is log omega over times k. K is Boltzmann constant. Then that is omega. That is entropy. This is a definition of microscopic entropy. Then this formula actually is ds over dE. ds over dE is actually defined by, in thermodynamics, it is kT 1 over kT. So we have this relationship. Actually, inverse of temperature is just the derivation of the d log omega over log dE. Actually, this is a microscopic definition of a temperature, macro quantity T, and relate to this micro quantity omega. Actually, in this relation means this relation means T1 equal to T2. In thermal equilibrium, two systems has the same temperature. This is condition of the thermal equilibrium condition. This extreme condition means two temperature in thermal contact, in thermal equilibrium, their temperature is equal each other. Here is an example of the microstate. Actually, this is correspond to omega 1 E1. I using the E1, and here is omega 2 E2. Here is E2. Then actually this is our system. This is actually your environment. Then in here, each rectangle corresponding to one of the this is 잘못 그렸어요. 이렇게 하나로 그렸는데 one of corresponding one unit of the energy, and 뭔가 그림이 좀 잘못됐네요. 이게 아마 이게 렉탱글이 2개 있고 렉탱글이 3개 있고 이렇게 돼야 되는데 숫자는 맞는데 지금 이게 그림이 좀 잘못됐습니다. Maybe when I copy this figure, they are changed. So anyway, it has a unit of energy 2 means 2 block is one block corresponding 1 unit of energy. So if the system 1 is in energy 2 stage, then your total energy E equal to E1 plus E2. Then our total system has a total energy is 10,009 energy. Then to satisfy this energy, total energy, E2, E1 is equal to, then the corresponding E2 is 7. So this state actually combine this one. This state combine this one. This state combine this one. So your product omega 1, omega 2 maximize. That is your equilibrium state. And so some system is in the more probable than actually in our next lecture, we will describe the probability, then the micro state of the, you can find some states of the in equilibrium that corresponding to omega 1 omega total number of omega 2 corresponding to your energy stage, finding of energy stage. Anyway, this is one of the possible combination of the system and reservoir. Okay, then here is one easy derivation of a canonical ensemble. Here we consider, here is one of the E2. E2 is very large, so it is heat reservoir at temperature T. And our system, actually E1, actually this is E2. Then only a single state, it has energy 1. However, in assume, we assume here single energy state. So omega equal to 1, omega 1. This is omega 2. Omega 2 is we describe just omega. It is E minus epsilon. Epsilon is small quantity compared to this energy. This is actually probability that system has energy E. The your probability P epsilon is just heat reservoir energy state times your system's energy state. Then you can epsilon here actually epsilon is over E is a very small quantity because heat reservoir energy is a very huge number. So you can let's take actually omega is very huge number. So we consider logarithmic of the omega. Then we expand the tail expand to the epsilon. Then you can easily expand zeroth order term and first order term. Then our previous definition, this is 1 over kt. So second term changed like this one. Then you recover the original form of the omega, then it is omega e times exponential epsilon minus kt. Then the probability that system has energy epsilon equal given by this one, because this quantity at the total energy E is a constant. So it is proportional to the exponent of minus epsilon over kt. So this is actually important factor to decide your probability that system has energy epsilon. This is it is called this is actually this probability distribution is called Boltzmann distribution or canonical distribution in the canonical ensemble. So the PE actually as a function of energy epsilon is exponential form. That means at the low temperature energy will be higher probability. However, at given temperature, higher energy will be low probability. However, this exponential form shows so that this decrease is very sharp, but depend on the temperature T. At the high temperature, if T goes to the very large value, then it is this distribution function became more flatter. Flatter means all of the states had the same probability. So at the high temperature limit, every state has the same probability. However, low temperature, their inequality is more 분명하다. 지금 분명합니다. 제가 지금 단어가 생각이 안 나가지고 그렇습니다. So if in canonical ensemble, if a system is in contact with the heat reservoir, then the system at the energy state ER, R is your micro state, describe the micro states. Actually, this micro state is described by some quantum number in quantum state or in some phase space in classical system. If energy is described by discrete states, then your probability is P epsilon R proportional to e to the minus epsilon R over kt. So if you write this equation to the equality, you have some constant. This is C is normalization constant. The normalization constant is decided by summation sum of the all probability equal to 1. So C is one of this summation. So we call this summation is partition function. So your probability at the microstate R is proportional to the Boltzmann constant divided by partition function. Actually, here we write the partition function G. G is in the German language is Zustand humor means sum over states in English. So we use the G. It is called in partition function. 우리말로는 분배 함수라고 부르게 되는데 that reflect the way in which the G measure how energy is partitioned between states of the system. Actually, partition to the low energy is more probable. So it has this partition function has a meaning of this meaning. Then our statistical mechanics is you have a two-step solving the statistical mechanical problem. First, you down the partition function G. Then after that, write down the partition function. Then you have to obtain some function, some quantity from this partition function G. Actually, so in statistical mechanics, the main problem is to calculate by analytically G. If you don't solve the partition function by the analytically, then you can also solve the partition function by the numerically or simulation, like a Monte Carlo simulation. Actually, this is actually we call the statistical mechanics. 어떻게 강의를 하다 보니까 아주 길어졌네요. 오늘은 이번 시간 여기까지 해서 마치겠습니다.